Pretty much our entire digital world, we're talking secure banking, private messages, all of it, is built on a foundation of absolute mathematical certainty. It's this special kind of math that's perfect, totally error-free, and it's the secret behind what makes codes unbreakable. So what is this perfect math? Well, let's dive in and find out.
So what is this secret sauce, this hidden mathematical engine that's protecting your most sensitive information every single day? We're about to pull back the curtain on the invisible math that really runs our entire digital lives. I mean, we're talking about the heavy hitters of digital security here. You've got AES, the stuff that protects government secrets. You have RSA and SSH that secure your internet connections. Even the super powerful elliptic curve cryptography used in things like Bitcoin. The thing is, they all share this common hidden backbone, a fundamental set of mathematical principles.
Okay, so here's something you've got to understand that's absolutely crucial. Most of the computing we do can get by with really high precision approximations. Close enough is often good enough. But in cryptography, there is no close enough. A single tiny error, one misplaced decimal, could bring the entire security system crashing down. Nope, it demands absolute perfection.
And just so you know where we're getting this, a lot of what we're talking about today comes straight from the work of Professor Avi Kak at Purdue University. We're digging into his lecture series on computer and network security, specifically his lecture on finite fields, to really understand this perfect math.
All right, to really get this, we've got to start from the ground up. Think of it like we're building a rule book, step by step. And we're going to start with the most basic building block of all, something called a group.
So, super simple. A group is just a bunch of things, could be numbers, could be whatever, and one single way to combine them, like, say, addition. But, and this is the key, they have to follow a really strict set of rules.
Okay, so what are these rules? There are 4 of them. First up is closure. This just means if you take any 2 things from your set and combine them, the answer is also in the set. You always stay inside. This is so important for crypto because it means everything is predictable. Next is associativity. It just means the order you group things doesn't matter, which keeps calculations consistent. Third, you need an identity element, kind of like a 0 that, when you use it, doesn't change anything. And finally, every single item needs an inverse, an opposite that lets you perfectly undo the operation. I love this analogy. Think of it like a playground, but there's only one game you can play. And no matter what you do in that game, you can never, ever break these 4 rules. And you can never leave the playground. It's a completely self-contained little world.
All right, so we've got our playground. We've got one game with 4 rules. Now, let's add a second game. We're going to climb up this ladder of ideas to something a little more complex called a ring.
So a ring takes what we had, specifically, a special kind of group where A plus B always equals B plus A. The order doesn't matter. The big deal here is we're adding a whole second operation, multiplication. And as you can probably guess, this new operation has to follow its own set of rules. And no surprise, these new rules for multiplication probably look pretty familiar. Just like with addition, the set has to be closed under multiplication. It also has to be associative. And, this is a big one, the 2 operations have to play nicely together. That's where the distributive property comes in. So let's go back to our playground. We've just added a second game. So now we've got addition and we've got multiplication. And we have specific rules not just for each game, but for how the 2 games are allowed to interact with each other. Okay, our system is getting way more powerful, right? But there's this weird little loophole we need to slam shut. Our next step up the ladder is creating something called an integral domain. And it's all about making sure the number 0 behaves exactly like we expect it to with absolutely no funny business. So what is an integral domain? Well, it's basically our ring, but with one extra super important rule added on top. It has no 0 divisors. Now that sounds technical, but the idea behind it is actually really simple and really important. And what that means is actually something you've known your whole life. If you multiply 2 numbers together and the answer is 0, then one of those original numbers had to be 0, period. There's just no other way. You can't multiply 2 non-zero numbers and magically get 0 as the answer. And that right there, that's why this is a huge deal. It eliminates all sorts of weird mathematical loopholes. It makes our system totally predictable and stable. And that kind of predictability is totally non-negotiable for building solid encryption. Okay, we've been climbing this ladder, right? Adding rules, making our system more and more solid. And now, we've made it. We're at the top. This is the perfect playground for cryptography.
we've arrived at the field.
So what's the last piece of the puzzle? What's the one thing that takes us from an integral domain to a field? It's this. Every single element in the set, except for 0, has a multiplicative inverse. It has an opposite you can multiply it by to get back to exactly 1.
And why is that so awesome? Because it means we can finally divide perfectly. Suddenly, all 4 of the basic arithmetic operations, addition, subtraction, multiplication, and division, they all work flawlessly inside our little self-contained world. No errors, no close enough, just pure mathematical perfection.
So let's just take a quick look back at the ladder we just climbed. We started with just a simple set of things. Then, by adding rules, we built a group, then a ring, an integral domain, and finally, we reached the top with the incredibly powerful and perfect field.
Okay, I know that was a lot of abstract stuff, so let's use a real example. Think about the set of integers, all the whole numbers. It's an integral domain, but it is not a field. Why not? Well, take the number 3. Its multiplicative inverse is 1/3, right? But 1/3 isn't an integer. You have to leave the set to find it. Now, what about the set of all real numbers? Yep, that is a field, because the inverse of any real number you can think of is also a real number.
And look, if you're thinking, wow, that's a lot of theory, just listen to what Professor Kak himself says about this. He doesn't mince words. He basically says, if you don't get these concepts, you might as well forget about learning computer and network security. It's that fundamental.
So, let's bring it all home. What's the big takeaway here? We've just walked through how to build a perfect, self-contained mathematical world from scratch. A world where all the basic math works flawlessly, with 0 errors. And it's this predictable, perfect environment that is the absolute bedrock for all modern encryption.
So we've pulled back the curtain on this one piece of invisible math that keeps us all safe online. And it kind of makes you wonder, right? What other invisible mathematical structures are out there quietly running all the technology that shapes our world?